Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast. We're going to talk about an unusual interpretation of DNA inside our cells, and that it may be an antenna, a double-helix type of antenna. So I'll let you describe it, but thanks for coming. How are you doing?
Not bad. How about you?
Very good. Yeah, this is a very intriguing idea. So tell me a bit about your background and how you first thought of this, or is it your is it the professor that's running the experiments that thought of this?
I find out this antenna thing is very interesting because it sends signals to a very long distance. It sends the electromagnetic wave. And then I find out that even the word of antenna is inspired by the nature things. We know that there are antennae on the head of insects. They use it to detect chemical and mechanical signals from the environment. So we know that in this way, we know that many antennas are also inspired by natural things. So we designed an antenna inspired by DNA. You know, the DNA is shaped of a double helix. It has base pairs in front of the double helix. And the function of DNA is determined by those base pairs. So we designed an antenna like that. It's also double helix shaped. Then we put a base pair inside this antenna. The location of the base pair decides the function of this antenna. So now this antenna is multifunctional, and the function can be adjusted very easily.
Well, what is important about the double helix structure of an antenna in general, with or without base pairs?
It sends strong signals, and then it has multi-functions. So it's very reconfigurable and flexible. Whenever you want to use a function of an antenna, you can find the right location of the base pair. So you can adjust it to become the antenna you want. So it's an all-in-one antenna.
When you say base pairs, what are you using instead of base pairs, and how many different kinds of base pair-like insertions do you have?
We have three kinds of base pairs. Either it's a capacitor or resistor or inductor. So different base pairs can give different functions of the antenna. So basically three types of functions.
Oh, okay. How tightly is the double helix antenna coiled? Like, what is the spacing between turns of the antenna?
Basically, you can manufacture it from very small, like nanometers, to very large, like centimeters. The size of the antenna determines the frequency band it works on.
So is the antenna, what is it tuned to specifically when broadcasting, and what is it tuned to when receiving? If you make it the same size as it would be in a DNA molecule, what frequencies seem to be broadcastable and receivable with that size of a shape of an antenna?
So if you manufacture it very small, then the frequency band will be very high. If you manufacture it to be large, then the frequency will be very low. That's a basic principle.
Right, but when you look at the actual size of DNA, have you made an antenna that is the same size? Or can you estimate mathematically, if you did, what frequencies would be the best broadcast and received by a DNA-sized antenna, literally?
That will be hundreds of terahertz if you can really manufacture it like that. And we know that So basically the wavelengths. So there are two concepts. There is a wavelength and there is a frequency. They are basically the inverse of each other. So 1 over wavelength is approximately the frequency. So if you manufacture the wavelength size of the antenna very small, it means the wavelength is very small. Then it means the frequency is very high. So it can achieve terahertz or even hundreds of terahertz if you can really manufacture your antenna in the size of a DNA.
Wow. So what does this tell you about biology? Do you think that DNA inside of our cells actually does act like an antenna?
you can use antenna. You can use DNA as an antenna. And I think people would rather manufacture antennas shaped like DNA rather than using DNA as antenna because it's hard for DNA to carry the electrons to run on it. But I think you just offered a very good idea. If we really do that, I think it still works, but the efficiency might be low than the metal antennas.
Well, that's okay, but again, now that you've made some double helix antennas, if you calculate what an actual antenna, if DNA could act as an antenna, what do you think it would be useful for? Could it broadcast over very short ranges? Would it, if it broadcasted, would that have so much energy that it would destroy the cell that it's in? Like what kinds of electrons would be needed and what energies in order for an antenna like that, of that size and shape, in order to work?
I think you just brought many interesting points. Like we know that this range of this signal will be short, but we know that in our daily life, we use something like RFID. Like when you buy stuff from the supermarket, you want to swipe the barcode scanner. And now you want to put the barcode very close to the scanner so that might be a use of this DNA antenna. Although the range is short, we can still use it for scanning things. So that is possible, that is applicable. And we also know that now in the modern world, we want to make things very small. We even want to wear them so that a DNA-shaped antenna can be made very small to be integrated on our wearable devices. So that is not only applicable, but it's also very useful.
Inside of our bodies, to me, it looks like our lungs are antennas for broadcasting the oxygen we breathe in. But they are also antennas in collecting the carbon dioxide and, broadcasting it back out in one stream, through our mouth. And our bloodstream also appears to be an antenna because it broadcasts, the oxygenated blood out to all our cells. And then in reverse, it takes in, the cellular debris and other, the deoxygenated blood back from our cells and aggregates it back in. So do you think that there are many antennas in our bodies and other creatures' bodies, or do you think that DNA is the only one that really resembles an antenna?
Thank you for bringing that. It's really interesting that you mentioned that there are two types of antenna. One, we use it in two ways. One to deliver signals, like just as I said, the antennas on the head of the insects. They use it to test the background, to test the environment. And the other type of antenna sends energy or stuffs, like what you just mentioned, to deliver airs, to exhale and inhale. So in that sense, yes, our lung can be seen as a type of antennas. And then it's not only DNA, but many other things in our body can be seen as a type of antenna. And we can definitely inspired by them to make our electronic devices or mechanical devices.
Well, what else in the body do you see as an antenna, that in addition to what I said?
Our eyes are actually perfect antennas. We receive the light signal. Light is actually a kind of electromagnetic wave. So our eyes are designed so perfect, we can see things very clear. So far, I don't think any man-made structures can achieve that precision and wide angles. So our eyes are definitely good antennas designed. And also our ears receives the sound signal, which has a longer wavelength. So, the frequency will be lower. And it's also a very good antennas. And it's an antenna array. So we have 2 ears, which can then receive the signal so that we even know which direction the signal comes from, even if we close our eyes, just by our 2 ears. So they are really well-designed antennas.
Is there a specific name for an antenna that, transmits as well? Or, only one that receives? Or is it just called a bidirectional antenna? Or is there a special name?
Good question. It's a really good question. Any antenna is bidirectional. If you can receive a signal from that antenna, you can transmit the signal from that antenna. And the frequency of the received signal and the transmitted signal will be the same.
Okay. So what kind of experimentation are you doing with these double helix antennas? What are you trying to figure out by making them?
we want to figure out that a concept that, now we have a trend when we design or invent our electronic devices in our house. We are so excited. We have many electronic devices in our house, but then we find out we are overwhelmed by them. There are so many of them. So there's a trend that we want to merge the electronic devices. But common idea is that we make things small so that we can integrate them together to make one thing and for all. Like if you look at your phone, it's not only a phone, it's also a camera, it's also a PlayStation and many things. But then when you integrate them together, you have many antennas. So the common idea is to make the antenna small, but we want to present another concept. Instead of make them small, you can make them less. You can make one antenna has many functions so that whenever you use a function, you can tune the antenna to that function. That's the basic concept of our antenna.
How do you tune an antenna? Do you change the spacing between the coils of it? If it's a double-helix antenna, or like how else do you tune it?
Good question. So definitely tuning the space between the double helix would change the function. However, it's very hard to do that in real life. So that we designed the double helix antenna with the base pair between the double helix, so that when you change the location or the different base pairs, the function of this antenna will change. And changing base pairs is much easier than changing the space between double helix. So that's a reconfigurable antenna, but it's very easy to tune.
Well, also in the body, we have fractal antennas. Our bloodstream, our blood system, our lungs. A lot of it seems to be fractal. The double helix, it's probably not fractal, but have you tried to make a fractal version where you have a double helix and then it splits into two double helix and it splits again and again, and to see what kind of benefits you get from doing that?
I haven't tried that yet, but I think you offered a very interesting point, and I think that's definitely feasible and applicable.
Okay. So when an antenna is tuned specifically for, a certain frequency range, are there also, lower frequencies that are resonant with the same antenna? Or is it very, very tightly defined and only a certain range of frequencies will affect it?
Actually, if you do it well and you design it well, any frequency band is possible. But the frequency band is usually dictated by the applications. For example, if you use it on your phone, you specifically want some megahertz frequency. And if you tune it to your televisions, it's a slightly different frequency. So the design is basically dictated by the application. If you want to go to the bioimaging, then you wanted the frequency to be very high to see the cell, to see the DNA. So it's based on the application.
Well, the reason why I ask is that DNA inside of us, it may not be broadcasting anything, but what if there are lower resonant frequencies of EMF that it can take in and it does affect our DNA? If it would broadcast in the terahertz range, perhaps there's a gigahertz or a megahertz or a kilohertz set of frequencies that would also cause our DNA to act, to unwind or to change or to do something, upon receipt of those frequencies that are resonant.
I think you brought a very interesting point. That is totally possible, but don't forget that DNA usually works as itself, but our antennas usually works in a system. We also need transmitters, the signal creator to work as a team so that we are sending signal not only from the antenna, but also from some signal generating devices. So that to achieve that, what you just described, it is totally possible. But we should design some devices that uses DNA to transmit the signal or receive signals from DNA to that device. I think that now our technology can definitely do that, and I think that's a feasible idea.
Well, also too, DNA can unzip and then come back together. So have you tried with your antenna, let's say it has 100 turns of coil and there's base pairs in each turn. Have you tried disconnecting, let's say the middle third of coils so that you just have, the antenna kind of breaks into two and then comes back together, and seeing how that affects the use of it? That would emulate maybe what DNA does,
If you like this podcast, Please click the link in the description to subscribe and review us on iTunes.
Exactly. You asked a very interesting question. There are many types of antenna. One, you can use a single helix antenna. You can also design a double helix antenna. Both of them works. So if you break them up, they will show different properties, and they show different functions. That's also a way to tune the antenna. You've really brought a very interesting point. It's possible, yeah.
Yeah, if you decide to make one that skips every other turn, that disconnects every other turn, what would that do? That disconnects a middle piece, that disconnects every third turn, or, chunks of turns. I guess there's a lot of experimentation you can do to see what the effects will be.
Yes, I think that will be an interesting future direction to test the DNA when they got from 2 helix to 1 helix, and then to see what the antenna what type of antenna is like. I think that will be a very interesting experiment.
Are there any man-made antennas that can transmit and receive in the terahertz range, or the hundreds of terahertz like DNA may be able to do?
Yes, there are a few types of antenna that already been fabricated, but not DNA shaped. They are called bow tie antenna, which is a common antenna that can be easily fabricated. And there is a dipole antenna. You can see it in real life. It's like you can see it on the top of your car, but it's different frequencies. If you want it to be working on higher frequencies, you have to make it very small.
Well, what would be useful, or what is interesting or different about transmitting and receiving in terahertz and beyond? What is it used for anything commercially right now? And are the physics unusual or different with things in that frequency range?
Thank you for bringing that. Yes, what you just brought is actually a very hot topic recently. It's called nano antennas. So we want to make antenna very small, working in a very high frequency band, so that we can basically as we already talked, the range of the signal now becomes very short. Use it as a probe and to get it very close to the target. So it's usually used in bioimaging. You can make the probe very close to the cell you want to test and then to image those cells. So basically it's on bioimaging.
Oh, really? Okay. Well, what is the range of 1 terahertz to 100 terahertz signal? How far away from the antenna could you measure?
That's an interesting question that you can actually calculate it by your hand. It's speed of light over the frequency. You can use that equation to approximate the range. So basically nanometers.
Oh, wow. Okay. So again, if DNA was an active antenna, it would only transmit maybe 50 nanometers or 100 nanometers? What is your guess?
It's possible to even achieve micrometers. You have to make your signal very strong. And then you also want to avoid the antenna being destroyed. So probably 1 micron is the upper limit.
Oh, very interesting. Huh.
Yeah.
And how much energy does it take to produce, to cause an antenna to broadcast a signal for any length of time in the terahertz range? Does it take a lot of energy?
The thing is, if we use a common device like our phone or a computer to send that signal, definitely the DNA will be burned. So required power is actually extremely low. So you don't have to worry about the energies. But instead, now you want to control the energy to be very low so that you don't burn the DNA.
Do you express the energy in terms of volts, like electron volts, or how do you express the amount of energy needed and how much is it?
I think it's very small and down to the electron volts. But I'll put it in this way, probably 1/1000 of the common currents or voltage running our computer. So we want to keep the voltage thousands of times lower than that.
Oh, okay. So the voltages inside a computer are, let's say, 1 to 5 volts. Biologically, in order for them to not fry the DNA, they would need to be like, 1,000th of 1 volt? I guess a microvolt, right? Well, that'd be 100,000. Yeah. At least a millivolt, but probably millivolts to microvolts, right?
I believe it has to be even smaller than 1 millivolts. Probably several microvolts will do the job.
Huh, interesting. The reason why I ask is perhaps biology is capable of producing, that voltage easily. I guess if you look at cell membrane potentials, I don't know how strong they are in terms of volts, millivolts or microvolts, but these potential differences may be producible by internal processes in a cell, which would allow activation of a DNA antenna. And again, I'm just speculating, but it's a thought.
Yeah, it is possible. I don't know whether nature is really doing that, but if we humans want to manufacture something like that, hard part will be controlling that signal, because the signal between cells or neural systems are hard to control. Or if we make a device of our own that produces the signal like that, it will be very small and hard to manufacture. But I think the technology now allows us to do that, although it's very hard. Yeah.
Well, our bodies are very electrical. I mean, our heart,
Yes.
it's controlled. It has a whole electrical control system, our brain, our nervous system. So maybe it's not so crazy. Maybe this is, an unknown way that our bodies operate.
Yeah, that is possible. And I think researchers should take it seriously to do experiments on that.
So what's next for your experimentation? What are you going to be looking at?
So there are two ways to carry on the research. One is to make it very small so that we can do bioimaging with it, or even some other applications. Or we can try to merge more antennas to make this antenna even more multifunctional, contains even more functions, so that when we are designing our household devices, we can merge more antennas to make things very small, applicable, like on our phones. I think that's two possible directions.
Yeah, what are some of the functions of an antenna? You've referred to this a few times, broadcasting, receiving. I mean, what other functions are common to antennas?
So basically, you can design very narrow band antennas, which works only on one specific frequency, or you can design a very wide band signal antenna. For example, then a wide band signal will sounds like a burning tone, a tone from your telephone, so that it's beep, something like that, and they are sending different signals, and the code carried by those signals are also different. So in short, different functions of antennas carry different types of codes.
What's the information capacity of various antennas? Can some carry a lot of information? And do they have to be broadband antennas, or the narrow ones carry a lot?
Yes. How about I put it in this way? Narrow frequency band antennas are usually used to carry out information. Like right now, we are talking, we are sending our sound signals and transfer it to electronic signals to each other. That's when we use a short band frequency signal. But a broadband, then you can transfer something like pulses. And there is a common application we can think of is the Morse code. In Morse code, we just click with pulses so that the signal is more clear, is more distinguishable, but the information will become less.
Again, if we look at DNA, and you have to speculate here, I know, do you think it is a very narrow band antenna or a wide band one? When you look at it, the size, the shape, the dimensions, what do you think what's your guess on its abilities?
Good question. I think it will be wideband, sending pulses, because only the thing humans design will be shortband. But in nature, we usually observe wideband signals like pulse, like when the animals are shouting, or when an elephant is like stepping on the ground trying to send signals to the other elephants. You usually observe broadband signals rather than shortband signals. So if DNA is really sending a signal, I bet it's broadband.
If it is sending signals, what would be the receiving structures? Let's say it only can send signals out to the edges of a given cell membrane and no further, but a lot of the signaling would be internal to the cell itself. So what would be recipient structures, like receiving antennas, if you would guess?
I really like your question. It's really inspiring. Like I said before, an antenna good at sending signals is also sensitive so that it can receive a signal. If DNA is a good antenna, then it must receive and send signals. So the receiving antenna from a DNA signal will be another DNA.
I guess it could be maybe RNA as well, because RNA is probably present in many places around the cell, or perhaps proteins could act as receivers. I don't know. They're very complicated. But.
In antenna design, we usually talk about the concept of matching. Your transmitting antenna should match your receiving antenna. So when talking about matching, we usually talk about frequency matching, frequency band matching. So usually they're in the same structure. So if we send signal from DNA, we really want to receive a signal by DNA. Yeah.
Okay. Interesting. I guess perhaps DNA, our DNA being so long, one part of it could transmit to another part instead of having to, if it's many, many base pairs away, if it's, thousands or tens of thousands of base pairs away, perhaps it's transmitting to another part of it, or one chromosome is transmitting to another, but who knows? I don't know.
Yeah, if that happens, that will be a very big discovery, and it will be very revolutionary if we really find that phenomenon.
If DNA does send or receive, what would you expect to see when the DNA sends and receives? If it does, would you expect a change in the shape? Would you a temporary change in the shape? Would you expect increased vibration of the molecules? Like, what would you? I know this is probably not your area, but what would you expect to see?
Good question. You just mentioned one of the possible phenomena, the vibration of the molecules, because there are two types of signal we can think of. The first one is electromagnetic signal. The second is mechanical signal. So mechanical signal means vibration. So you can, if that happens, you will observe similar vibrations on the receiver antenna and transmitter antenna. But if it's electromagnetic wave the signal is, then you will observe electrons moving very fast on the antennas. That can be tested by the electromagnetic scattering phenomena from the DNA. That is totally possible to detect. Yeah.
Well, also too, so I'm imagining the DNA sitting in a thick, viscous liquid, like the cytoplasm. So if it's transmitting or receiving, it would be vibrating. But I would think that the cytoplasm couldn't vibrate, obviously, in the terahertz range. It would dampen the vibration. So then if I imagine, let's say, an antenna in the air, the air has a certain density. If I have an antenna here at ground level versus an antenna up on Mount Everest, there's a big difference in the density of the air. Does that affect the operation of the antenna? And the reason I ask is that how would the cytoplasm around DNA, let's say, affect the operation of a DNA antenna if it worked?
You brought a good question. Yes, definitely the environment will affect the performance of the antenna. But what's more like not only the density of the air, but also the shape of your mountain and the shape of your ground will also affect the performance of the antenna. So if we are talking about sending signal from a DNA and receiving signal from a DNA, then the shape of the cell might matter. But remember this effect will be very small because more than 90% of our body is water. And the water can be seen as a homogeneous medium. So I think it is not a problem. The variation of the environment near DNA can be seen as ignorable. You can ignore that.
So are there antennas that work underwater? And if so, how are they different from ones that work in air?
Good question. We talked about two types of signals that can be transmitted. First one is electromagnetic signal. The second is vibration signal. The vibration signal can be operated underwater because water can propagate vibrations. But the electromagnetic wave will be harder because water absorbs those waves. So if DNA is sending or receiving signals, a vibration wave will be easier. Otherwise, the signal can only propagate in a very, very short range.
Oh, so it could be vibrational instead of EMF.
Exactly, yes.
But would the vibration have a terahertz range frequency, or would it be a lot lower?
It depends on what is vibrating. So if smaller structure is vibrating, for example, the molecules on DNA, then you see the vibration will be very short. Then the distance of this vibration will be short, so that the wavelength is short, so that the frequency is higher. But if is the whole DNA vibrating? You see this vibration amplitude is much higher, then your wavelength is much higher, then your frequency is much lower than that. So it totally depends on what is vibrating, whether it's molecule or DNA itself.
Huh. Okay. I guess there's many things to figure out, but so you're trying to make you're trying to get as close as you can to the size and shape and environment of DNA itself, or are you just using the morphology of DNA as a double helix to experiment with antenna design on larger sizes?
I think both are applicable, and they can be used in different applications. Like larger antenna can be used in our daily devices, but smaller, like antenna with a similar size of DNA can be used as used in bioimaging field, or even like if you really use a DNA as an antenna, then it definitely can be used as detecting DNA itself.
What kind of bioimaging do you think will be the first thing that could be accomplished with very, very small antennas?
Imaging cells or imaging DNAs, RNAs, yes.
When you say imaging, how fine of a resolution do you think you could get?
Theoretically, the resolution is very close to the wavelength of the signal, and the wavelength is dependent on the size of your antenna. So if you are using a DNA as an antenna to send signals to do imaging, your resolution will be very close to the size of DNA. But that's theoretical. Oh, wow. Yeah, in real world, there will be noises to make the resolution worse than that.
Right, yeah. Wow, very interesting, very interesting. I'm glad I had the chance to talk to you. Is there anything else I should have asked you I haven't? Any other important points you want to bring up?
I think you've brought many interesting ideas. I just hope that you continue to think that way. And I think there are many good questions you have brought up. I'm really astonished that you have many ideas.
Oh, well, thank you.
Yep.
Well, very good. Thank you so much for coming on the podcast. I really appreciate it.
Thank you very much to invite me.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.